All right, so guys, we're studying dynamics today. Dynamics is also a branch of physics that specifically deals with forces and their actions on the bodies that are in motion, right? So let's learn the basics of forces first of all. From the very basic definition, a force is explained through a push or a pull on an object, right? And the SI unit of force is newtons. So that push and pull can basically cause changes to an object. It can change the size of an object, the shape of an object, the speed of an object, the direction of motion of an object, right? So these are four physical aspects, physical features of an object that can be changed with the application of force. Um, and secondly, a force produces an acceleration. Acceleration of 1 meter per second square is produced by an application of 1 Newton force. Now, this 1 Newton force is a standard force that you're applying on an object, and you're assuming that, okay, because acceleration is the rate of change of velocity, so we're assuming that the object's velocity is changing by unit time. And the answer is 1 meter per second square, right? Similarly, a force is usually measured with the help of spring balance or a Newton meter. You can look at the diagram for spring balance here. This is a spring balance, all right, in figure 3.1. Or a Newton meter is also used to measure force because you see weight is a force. So now objects that have their weight have this gravitational force that acts downwards because weight is the pull of gravity. So you can measure the weights of objects through spring balance through a Newton meter. This is why these instruments are used for force measurement. So we're looking at some of the common types of forces, right? So the first one is weight, the pull of gravity. It always acts downwards, perpendicular, right? Then there's friction. Friction exists between surfaces when two surfaces are in contact, right? For example, there's a car moving on a road. The car's forward thrust acts towards the right hand side. The car's friction would act towards the left hand side. And this friction would basically be the opposing force over here, and it would just be generated through the contact between two surfaces. And that contact, yeah, okay, then there's tension. Tension is in a string or a spring. For example, you stretch, this is a point from where the spring is stretched, and you're stretching it to this side. Tension would act opposite to the force that's applied on the string, right? Similarly, if there's a spring here, assuming like this, and there's a mass, there's a weight attached that pulls the spring downwards, there's going to be a tension force acting upwards on the spring, all right, upwards. Then there's forward thrust. Forward thrust, the force that causes a vehicle to move. It could also be known as the engine thrust or the forward or any forward force. Then there is drag force. Drag force is the force that opposes the motion. And see, friction is a form of drag force. Any force, any opposing force could be a drag force. It could just be friction. It could be air resistance, right? So any force that opposes the motion, opposes the forward thrust force is known as drag force. Then there is contact force. So contact force is the push that exists when two objects are pressed against each other. For example, if there's a ground and you just place a box against the ground, there will be a contact force generated between the block and this surface, right? It's also known as the normal reaction force, which is against the weight because the weight acts downwards. This normal reaction acts opposite to the weight. Then there is resistance or viscous force. Viscous force is the opposing force found in fluids like water and oil. For example, if you have a glass of water here and you drop a ball inside it, the ball would travel to the bottom of the glass. Now, the time the ball would take to travel in this particular liquid as soon as it enters the glass and it touches the bottom, that is throughout this time, it's going to experience this opposing force called the viscous force or the resistance force, right? And it's also a form of drag force. Then there are electric and magnetic forces, which you're going to study in the upcoming topics. Now, let's look at the effects of forces on moving objects. So, forces can cause a stationary object to start moving. They can cause moving objects to move even faster, right? To gain speed. They can cause the objects to slow down, losing speed, and they can cause the objects to change their direction. So this is all the effects. And now to understand these effects in a better way, it's important to also understand the representation of different forces. Forces can be represented in many ways. Theoretically, you can represent forces in form of vectors. Vector diagrams and vectors are basically the ways you represent different forces on a paper. For instance, if you have this block and I tell you that there's a force of 10 Newton acting towards the right hand side, this 10 Newton force is the forward forces that is this, you can represent it through these arrows. And then if I tell you, because of the contact of this block with the surface, there's a drag force, there's a friction force of 5 Newton acting backwards. You can draw an arrow backwards and represent that force as well. Similarly, you look at these vector diagrams here. There are different vectors representing different forces. There's a 5 Newton force, there's a 3 Newton force. So in the first one, you see 5 and 3 both act in the same direction. So you add 5 plus 3 and you get the resultant force. Now, this column on the right-hand side represent all the resultant forces. Guys, resultant forces, basically all of these forces, which are sort of, you could say, the addition or the total sum of forces. Could be subtraction as well, or it's just a net force. Net force is either the added forces or the subtracted forces. Similarly, if let's say 5 and 3 act in the opposite directions, they're gonna get subtracted. So, but you see the resultant of 2 Newton is gonna be in the forward direction towards the right hand side, because 5 Newton was towards the right hand side. So this is why this force of 2 would also be towards right. Then you see in the third case, 3 and 3, both of these forces cancel out and the resultant is 0. Now, there are some ways of finding these resultant for or drawing these vectors on paper, right? One of the ways is the parallelogram method, parallel, and the other one is a head to tail rule. So remember, parallelogram method is not recommended because it requires a lot of geometrical instruments to actually draw. I would suggest go for the head to tail rule if, let's say, it's required in the paper. Head to tail rule is simply when you add the vectors, okay, I'm gonna, let me see if there is an explanation of this any further in the notes, which I don't think there is any. All right. Let me just explain it on my own then. So in the head to tail rule, the head of the first vector, this is known as the tip, the head. The tip of the first vector is joined with the tail of the second vector. So if you join tip and tail, the resultant is going to start from the tail of the first to the head of the second, like this. So this is vector 1 and this is vector 2. So the second vector is joining with the tail of the first vector, and the resultant is getting originated from the tail of the first vector to the tip of the second vector. All right, this is resultant. For example, in this case, 5 Newton is the first vector. So the tip of the first vector and the tail of the second vector, which is 3 Newton, are combined. And then there is a resultant. This is resultant force. Let's look at Newton's third law of motion. Newton's third law of motion states that if an object A exerts a force on another object B, then object B will also exert an equal but opposite force on object A. Every action has an opposite and equal reaction. For example, a table. There's a book placed on table. Now this book is exerting a force. Look at it. Let's zoom it in. Guys, hold on. There's So I was explaining that assume if you have got this book, now the book exerts a force on the table, and the table in return exerts a force on the book. Force A and force B are opposite and equal. So opposite and equal forces, this is the concept of Newton's third law, all right? So to every action, there's an equal but opposite reaction, right? Newton's third law of motion describes 4 characteristics of force. Now, what do you understand about the force from this law? Number 1, a single force does not exist by itself. Look at this first law. A single force does not exist by itself, which explains that there is always another force to the single force. Forces always occur in pairs called action reaction. There's always action reaction. Then action and reaction forces are equal in magnitude, but they act in opposite direction. Action and reaction forces act on different objects. Yeah, this is very important. What if these objects acted on the same object? This is always a question when we study this third law as well. Um, why do these forces not cancel each other out if they're opposite, if they're equal, right? Um, like this. Now, both of these forces are acting on the same object. Why do they not cancel each other out? Because this is not the case for Newton's third law. Newton's third law states that the forces act on different objects. In this case, the book exerted its force on the table and the table exerted its force on the book. The forces were equal, they were opposite, but they were on different objects. Whereas what I've drawn here, this was not a case third law. It just was a violation of third law, in fact, yeah, where the forces were acting on the same object. Okay, balanced and unbalanced forces. Now, balanced forces cause no change in motion of an object. Guys, hold on. All right, guys, sorry for the interruption. Okay, so we were looking at balanced and unbalanced forces. Balanced forces cause no change in motion of an object, right? Because the resultant force is zero. For example, 0 meter per second square, right? Um, where acceleration is zero, okay? Now, under the action of unbalanced forces, object at rest starts moving. So when the forces are unbalanced, you see, if there's an object, there's a 5 Newton force, and now if you now let's put an unbalanced force of 3 Newton maybe. If you put it in the forward direction or even in the backward direction, the object, if let's say was moving, might start moving faster, might slow down. If an object was at rest, might start moving. So this is all that these unbalanced forces can cause. Resultant of balanced forces gives forth Newton's first law of motion. Now, resultant of balanced forces is zero, and the resultant of unbalanced forces is not zero. So when the forces are balanced, the resultant is zero, and you can understand this law through Newton's first law. And when the forces are unbalanced, the resultant is not equal to zero, and you can understand it through Newton's second law, right? So Newton's first law of motion explains that the resultant is zero. Newton's second law of motion explains the resultant of zero. And okay, let's try to understand this. What is Newton's first law of motion? That every object continues its state of rest or of steady motion in a straight line unless acted upon by an external force, right? So if an object is at rest, it's gonna stay at rest. If the object is in motion, it's gonna stay in motion until an unbalanced force acts on it. For example, a car. moving in a straight line. Okay, this is a straight line motion. A car moving at constant speed. What does that mean? That forward and backward forces are balanced. Maybe assuming if 5 Newton acts in forward direction, 5 in backward direction, what's going to happen? The car would continue to move in straight line, right? If it's rest, it's gonna stay at rest. But in this case, we're assuming that the car is moving. It's moving in straight line. It's gonna continue moving in straight line if there are balanced forces. Now, what if I tell you, yeah, I'm removing this backward force. I'm erasing it off. Let's erase it. Now, what's gonna happen? The forces are unbalanced. There's just 5 Newton in the forward direction. The car would just move in the, it would move faster because there is no resultant, there's no resistive force now, there's no friction, right? So this is what Newton's first law explains, that whenever there is unbalanced force, the object would change its speed. The object would change its position. That's very simple. Yeah. Now again, 5 Newton force acting on the car is moving faster. Now I'm adding a backward force again. Now there's a force that's resisting the car's motion. What's going to happen? Because these two forces are equal now, the car would now move at a constant speed. The speed of the car will not change. It is going to be moving, but it's going to be moving at a constant speed. This is what Newton's first law is. Let's look at Newton's second law of motion. Newton's second law of motion explains that in the presence of an external force, an object starts accelerating in the direction of applied force. The magnitude of this acceleration is directly proportional to the applied force and is inversely proportional to the mass of the object. Don't get overwhelmed by this statement. It's very simple. If whenever there is a force, the object would move in that direction. Yeah? If there's a box, you're pulling the box with 8 Newton force in the right towards the right side. Imagine you're pulling the string towards the right side. What's going to happen? The box will move towards right. Very simple. Yeah? Because this is the effect of force. And that force is going to be directly proportional to the acceleration, because you see, whenever the object is going to move, there's going to be an acceleration. So this force applied will be directly proportional to the acceleration of this object. Now, what does it mean? If the force is more, the acceleration is also more. If the force is less, the acceleration is also less. This is F equals ma. You must have studied this formula, where m is mass, right? F is force, m is mass, a is acceleration. One of the quantities will have to be constant to establish a relationship between the other two. Force proportional to acceleration, provided that the mass is constant. Mass proportional to force if acceleration is constant. But in this case, just focus on the first relation, that F is directly proportional to A and M is constant. Mass is constant. When can the mass be constant? If the object is the same. You cannot change the object. You're just talking about a single object, okay? So that is very simple. You see, if the forward thrust is more, the car was going to accelerate more. Very simple. Yeah, if you drive the car faster, if you press on the accelerator, it means that the engine thrust increases and the car moves faster, right? And why does an airplane move very fast, even faster than a car? Because it has greater engine thrust force. It has greater forward thrust. So when the forward thrust is more, the acceleration is also more. So force is directly proportional to the product of mass and acceleration. F equals ma. Again, mass and acceleration's product equal to force. If this is clear, we can move on to friction now. Friction. Force of friction is the opposing force that exists between surfaces of two objects in contact. We have just studied, I think I just gave you an insight into what friction is. A little more explanation could be that friction is always directed opposite to the direction of applied force. Very, very simple. The force of friction causes the objects to move slowly or to stop eventually, because it's a resistive force. It's obviously going to cause the objects to slow down. Force of friction causes, okay, yeah. Rougher surfaces produce more friction while smooth surfaces produce less friction. Yeah. So surfaces that are rough will produce more friction, and surfaces that are smooth will produce less friction. Why is that so? The reason is very simple, because rough surfaces, the irregularity between these surfaces is gonna cause the force of friction to increase. Now, friction does not depend on the area of contact, rather it depends on the normal reaction force. I'm going to explain that as well. So look at this formula. F minus FR equals MA. We studied F equals MA, which was very simple. You're applying a force and the object is moving. If the force is more, the acceleration is also more. But there is a resistive force as well. How can you forget the resistive force? Assume that this is a box and there is a forward force which is causing the box to accelerate towards the right hand side. There's an acceleration as well. But because the box is in contact, yeah, there's this surface with which the box is in contact. There will be a resistive force as well, Fr. Resistive force, or the force of friction, is represented by Fr. So when you look at the force, this F, this is technically the resultant force. And how do you get a resultant? By adding or subtracting forces. What are the forces? Forward and backward. So forward force minus backward force is equal to resultant force. This resultant is the F we talk about in F equals ma. So you need to resolve the forces first of all of an object and then take that final resultant force in this formula equated to ma. So this F minus Fr is technically the force you're talking about, which is the resultant force, equals mass and acceleration. So F minus Fr is the explanation of this capital F we're using. Yeah. So it is the theoretical explanation of the capital F, which is that F minus Fr equals ma, where F is the forward force and Fr is the resistive force, right? So technically it is the resultant force. Then there are different types of frictions as well. There's a sliding friction, there's a rolling friction, there's a drag friction, there's an air friction. Yeah, it all depends on the objects that are in contact. It depends on the surfaces that we consider and the environment, right? For example, if an object is in contact with a solid surface, it's going to have a different friction. If an object is in contact with a liquid or an air, it's going to have a different friction, right? So it all depends on the uh, types of objects. Yeah, just a second, guys. Okay. Um, then there's a rolling friction as well. Let's look at these. I think I'll just leave these for you guys to read, okay? I'll send in the notes in the group so you guys can just go over these definitions or even pause this video to actually read these right now, okay? Let's look at the effects of frictions. Um, there are different effects of forces of friction. For example, friction between soles and ground enables us to walk without slipping. Yeah. Then ridges in our skin of our fingers and palms enable us to grasp and hold objects due to friction. There exists a force of friction between tires and the road, which causes the vehicles to move. To reduce the speed of vehicles, brakes are applied, the brake pads rub against the wheels and produce a frictional force that slows down the wheels. Yeah, I'm gonna just move on to the next part of the lectures. Okay, effects of friction on the motion of a vehicle. Now we're assuming that a car is moving, and let's try to study what happens when there is friction. Okay, to stop a car, a force called braking force is needed. So this braking force is provided by the friction that occurs between the brakes and the wheels and the one that occurs between the tires and the road surface, right? So it's the basic friction, right, between the tires of the car and the road surface. Um, and when you apply brakes, this friction increases. Okay, whenever brakes are applied, the car doesn't immediately stop. There is always a thinking distance, and then there's a braking distance, right? Thinking distance is very normal and natural to humans because it is the reaction time that a human takes. So thinking distance is the distance traveled by a vehicle during the driver's reaction time. For example, if you're driving on a road and you observe a car accident in front of you, you won't immediately apply the brakes. There's going to be thinking distance involved. The time you will take to sort of react to that occurrence, the time you're going to take to sort of understand what's exactly happening and decide what to do, when to apply the brakes, right? So there's a thinking distance, there's a braking distance. You add these two distances, you get the stopping distance. Mm, an average reaction time is about 0.7 seconds, less than a second. Let's look at this diagram to understand the shortest stopping distance for a car on a dry road with good brakes and tires. If a car is moving at 60 kilometers per hour, it might, you see, cover 25 meters thinking and 31 meters braking. So stopping distance would be 56 meters. Car at 110 kilometers per hour similarly might take 150 meters to stop. So you guys don't need to remember this table. This is just to understand that this is the distance that you even cover when you try to stop, when the friction is in action, right? Okay. There are certain factors that might increase the stopping distance. Tiredness of a driver. If let's say the person driving is tired, so the reaction time would increase. Use of alcohol and drugs, distractions, mobile, music, movies, chatting, meeting, billboards. So any distraction may also increase the reaction time of the driver. So this is why it's advised to be very focused while driving, to avoid alcohol and drugs, and to be very active, right? Yeah. Poor road conditions, similarly, if the road is wet, slippery, the braking distance would increase. Poor brakes, size and mass of the vehicle, greater speed. So you see, 1, 2, and 3, these three cause the thinking distance to increase. 4, 5, and 6, they cause the braking distance to increase. And the last one, if the car is moving at greater speed, it will increase the thinking as well as the braking distance. All right. The circular motion is not a part of your syllabus. So we'll just generally study it. It is not, you'll study this in detail in your A levels, but we can just sort of look at it briefly because it is an extension of Newton's first law. I have to recap for you guys the Newton's first law. It stated that if an object is at rest or is moving, is going to continue to move or be at rest unless acted upon by an external resistant, unbalanced force. If the forces are unbalanced, only then an object is going to change its motion, right? So if you look at this example, where you're holding a ball with a string, and this string, you see, this is the direction of motion. This is how the ball rotates. Now there's a tension force in the string. And this tension force is essentially the unbalanced force. So T is the unbalanced force over here, right? Now, because of this tension force, the object is moving in a circular motion. This unbalanced force is causing the object to move in a circular motion. What if you cut off the string? If the unbalanced force is removed, I'm just calling it T. As soon as you remove T, the object is going to move in straight line. Why? Because look at F, look at velocity. Object's velocity in a circular motion at every instant is a tangent like this. This is the point, for example, draw tangent. This point, draw tangent. So let's say this is point A. If the string breaks at point A, look at the tangent. the direction of this tangent would represent the direction of the motion of that object from now on. So as soon as the string breaks, this ball is going to move like this in this arrow's direction. Why? Because now there is no unbalanced force. And Newton's first law states when there is no unbalanced force, the object moves in a straight line. This example is a perfect explanation of that. You see, you can try doing that. You hold a string, you tie a ball, you start rotating it with your hand and leave the string. As soon as you leave the string, the ball is not going to continue moving in its circular motion. It's going to move straight. It's going to move outwards, right? It can never happen that you drop a string and the ball keeps on moving around you. No, that's not going to happen. Why? Because it's against Newton's first law. And why is that so? Because there's no unbalanced force. An unbalanced force will always avoid a straight line motion. It's going to distract the object from moving in a straight line, right? It's going to either cause the object to change its direction. It's going to either cause the object to slow down. It's either going to cause the object to move faster. Remember previously we looked at this example of a car moving faster. Why? What was that? That was Newton's first law in motion, that was Newton's first law application, right? And that application stated that the car moving in straight line is going to move faster if the forces are unbalanced and the forces are in the forward direction. Similarly, this one is an example of circular motion. The result is that unbalanced force will always cause the object to deviate from a straight line motion. It's not going to let the object move in straight line, right? It's not going to let the object move um in a in a straight line motion. The unbalanced forces. An unbalanced force is what? It is a resultant force. To understand this, I'm going to just quickly read through the equation as well. The motion of an object in circular motion is called circular motion. The motion of an object in a circular path with uniform speed is called uniform circular motion. If an external force is applied on an object which is already moving in a straight line, in a direction perpendicular to its direction of motion, the object starts moving in a circular path. You see, this tension is the external force, and this is the object's initial direction, the blue line, and this force acts perpendicular, makes a 90-degree angle. Because of this, the object will move in a circular path. When an object moves along a circular path, the direction of its velocity at any instant can be taken along the tangent drawn at that point. Very simple. However, the direction of the resultant force is always directed towards the center of the circular path. Unbalanced force in a circular motion will always act towards the center. It is also called a centripetal force, by the way, right? Let's just move on. The next bit of dynamics